for this problem, we're going to do this part A of question 3. It says convert the decimal number below into an IEEE 754 single precision floating point number. So the first step to doing this is to convert this decimal number into binary. And so for the integer part of it, the non-decimal part of it, basically we're going to do this in pieces. So I can see this number is less than 32, and so there's not a 32 in it, but there's a 16 in it. So I can take out that 16, I'm left with 13. The biggest power of 2 that's in there is an 8. I'll take out that 8, I'm left with 5. Means there's a 4 in there and there's a 1 in there. And so I'm going to have a 1-bit set, not the 2-bit set. I'm going to have the 4-bit set, the 8-bit set, and the 16-bit set, and then a whole bunch of zeros in front of that. And then this decimal part, typically the process that I use to handle that works in general is I'm going to multiply that by 2, and if it's 1 or greater, I'm going to take off the 1 and continue this process. But it turns out it's not greater than 1, so I put a 0, I multiply what's left by 2, that gives me 1.0. This is 1 or greater, so I'm going to put a 1 and scratch out the 1, and I'm left with 0.0, and so the rest of it is going to be 0. So that's my binary number. I'm going to normalize this binary number by moving the decimal point 1, 2, 3, 4 points to the left. So that means, the normalized number that's equivalent is 1.110101 times 2 to the 4th. So I have my normalized binary number. So I'm going to refer to the cheat sheet to get the format of the IEEE 754 number. The sign bit is going to be just whether it's positive or negative. In this case, the number is positive, and so the sign bit's going to be 0. So here I'm going to fill in my answer. The sign bit is 0. And then there's an 8-bit exponent field, which is going to be filled in by E minus bias. So I know E minus bias is equal to 4. Bias says 127. So E equals 4 plus 127, which is the same as 131. And that's the same as 128 plus 2 plus 1. And so for my E field, which is 8 bits long, I'm going to have the 1-bit set, the 2-bit set, but not the 4, not the 8, not the 16, not the 32, not the 64, but the 128 bits set according to that. And so that's my 8 bits, 1, 2, 3, 4, 5, 6, 7, 8. And then I just need to take my, the remaining field in this IEEE number is the fraction field, which is going to be the remaining bits. That's 23 bits. And recall that the leading 1 is represented, we don't actually have to represent that leading 1 because it's understood for these numbers, so I'm going to leave off that 1 and I'm just going to copy over this part, 1, 1, 0, 1, 0, 1, and then, you know, I have to extend it with another 17 zeros. So 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And there is my IEEE 754 single precision floating point number.